All right, here we are. It's 5:13, class number 21. Coming down to the end here. What we got here? What is that? What is that at the bottom of the? What is going on? Look, look, there it is. Ha 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 ha. Seven more classes. I make them shout out stuff, but we'll hold off here. Okay. Now, tonight, your homework is to, well, blue day, I guess. But your homework is the flash off 7 to 7:45. Okay. 7 to 7:45. The address of the Zoom, of course, you know it. You're here. It's the same address as it always is, but it's at the top of the homepage. So you are free to bring anybody that's living at your house. Okay. Can't bring your neighbors. That's not fair. But anybody that's related to you, let's say, or living at your house, can play with you. They can sit in the room and they can tell you what it is. I think that may be the advantage. You know, crazy Uncle Eddie, I mean, he doesn't know a whole lot, but he knows his Doors, right? He knows his Led Zeppelin. So things like that. So I'll have music from Benny Goodman. I'll go back to Beethoven, all the way through Benny Goodman, through the Chuck Berry days, through 60s, you know, through the Pink Floyd journey, you know, all those 70s, 80s, Springsteen, and then on up into rap. And so hip hop, country western, of course, be represented. So I'll try and go through and pick up things in the time we have. I have like 500 songs, so we'll see whatever we get to in those 45 minutes. And it might even be the spoken word occasionally. Okay, so that's tonight. The winner, and if you guys win, then we'll negotiate. But right now, I don't know what I'm going to do if you win. I know what I'm doing if they win. All right. And if you don't come, you don't come. But now I emailed you back last night. Boy, it turned out to be a pain in the butt. I took all yours that you emailed me or you put on the canvas, and then I screenshotted it, and then I put that on my iPad, and then I graded each one of yours versus the key on the iPad, which that part was good. Then I took that, screenshotted that, emailed that back to each individual person. So all this process took 2 hours to grade a dozen tests. That's not too good. That ain't going, I cannot, that situation is untenable. But I wanted to see if it would work. And because when I teach online, that's probably how I'm going to give tests. And I need to be able to go back and forth. So it was a good experiment. I'll never do it again. But anyway, so you got your test emailed back to you with corrections, or me, not corrections, with me grading it. Now, Lizzie sent me a smart text last night. She said, wait a minute, am I supposed to then fix the picture you sent me, like print that off, fix it, then take a picture, send it back? No, not necessary. You can, now that I still have that. So I have your original test. So now you also have your original test, unless you're Eric or Takaki. And really, tell you the truth, neither one of them need to do any blue days. They're blue points. They're fine. But if you want to get blue points, a lot of you are at the 140 out of 150. I mean, come on, it's not worth it. Except that, oh, and you don't need to turn in your test because I already have your copy of it. So I'm fine with that. You can just hang on to it. But if you want the blue points, and remember, number 1 and 2 are not blue, everything else is blue. If you want those points, and that's going to help you a lot, then go ahead and go to your original test, look off the email that I sent you, see what you missed, and fix those problems. Then when you send me that, I'll compare that to, I'll probably download that and put that on my iPad and compare what you did to what your original was, and then give you the points. That's a lot of hassle for 5 points. Don't do it for 5 points, okay? At least 10. You already got the 10 out of 10. Everybody already had, unless you didn't turn the test in. Everybody's get a 10 out of 10 because I already have your test. Okay, so questions about all that. What do we got? We got 7 people here. Questions about that? Okay. Email me questions. To keep up, we finally finished 646, which means that now for virtual, you all must submit. And now I have this virtual, you will submit 6.4. It's worth 42 points. For 42 points. If you have it done, go ahead and submit it today, but it's due Sunday, the last day for not being kind of late anyway. You'd lose 5% a day after that. But Sunday, this coming Sunday, whatever date that is, what is the day? 13th, 14th, 15th, 16th, I think. Sunday, 5/16 by midnight. Get that in, and that's 42 points. If you don't turn it in, you lose 42 points. So this is trying to make up for all the stamps they get that you don't get. Now, I think we may have to turn in 6.6 as well, but let's get 6.4 turned in first. And then if we turn in 6.6, that'll be the last one you'd turn in for the year. But I'm assuming just to get more points in, we may turn in 6.6. All right. And believe it or not, they're still working. Meet table 4. I'm willing to meet one of you. I'll turn the recorder off. And if somebody wants to get met, now, if you get met, you give yourself, 12 Facebook points, 12 Zoom points just to get met. Let me pause the recording. All right, so here we go. Back to work here. Now, all these keys are posted. Every key is posted now up through 6.7, with one exception. 6.3 is not posted. And the reason is because 6.3 is fairly new. I have not made up a key and by the way, look at that. There's 6.7. So 6.7, those are the false statements. And my red there explains why they're false. So it's more detailed. And there's some pretty good details on 6.6. The back of 6.6 is really important. And 6.4, by the way, all of 6.4 is posted. I shouldn't tell you that because you're supposed to do it. But if you want to check your work, I mean, I'm assuming like honor system here that you're not just copying. All right. So the one exception is 6.3 and 6.3 right here. No, right. No, right. Okay. 6.3, I'm going to give you a chance to get some points on that. And so 6.3, we're going to make it a student key. And I've already had some students turn some stuff in. So 6.3 will be a student key. I'll take the best of. So if you turn in, like say you're really happy with 6.3.3, your boxes, you did a colorful job. It's very clear. I have mine, but I'm not real happy with it. It's not really well done. So like, or maybe you're on an iPad, you did it, like Rose and you do a really good job on your iPad. A really clear work. And you want to turn that in, you can turn in all of 6.3 if you want. Just email it to me. Then I'm going to pick and choose. Maybe one person gets all of them, but for them, I'm giving them, I think, 4 stamps per problem. So they could get 12 stamps, which is like 36 points. So for you, instead of giving you 4 stamps, I give you 12 points. Bonus for if I pick yours. Now, Avery Bozeman, who's like amazing, she's already sent in her choice for the first one, but maybe you could beat her out. I don't know. So yeah, so I'm accepting those for the next 48 hours. You just email me your key that you drew, and if I don't use it, I don't use it. If you just send it to me, I'm going to give you 3 points. They get 1 stamp. They just send it to me. You put your name in the running. And then, it's kind of cool because I'll put your name with it. And then you're, from now on, everybody that, if I'm teaching either online or at school, they'll say, oh, that was Sophia, that was Rose, that was Brandon, whatever, that did that. All right. So the rest of the keys are all posted. Did that. This, finally today, we had a little issue on, the reason why I didn't post it, didn't send you the emails yesterday, is because I noticed that on the website, there was no contact information. And I know that parents or you would go, okay, this is cool. I see where I sign up for it, but I have a question. And there's no, we need a frequently asked question. We do need that. We'll get that up there. That reminds me, I'm going to tell my boys to put that together. But there is now a contact. It's my email. So as you ask me questions, I'll start to put together a frequently asked questions. So now that's on there. So now I'm going to send this out today to like 5,000 people. Vera Rubin, we talked about her yesterday. She was looking for the ultimate gravity well. One thing I was reading about her last night, and her legacy, yes, she was sort of the mother of dark energy. I read a book once called 4% Universe. And there's a whole chapter devoted to, in fact, the book starts with Vera Rubin, and how she went out to find the center of the universe and ended up figuring and serendipitously kind of, quote, discovered dark energy. But probably what she'll be known the most for is what she did for women in astronomy and physics. On her deathbed, she died in 2016, like 50 different prominent women now that are in astronomy and all, owed their PhD to her, kind of, because without her mentorship, without her leadership, without her being a role model. So I thought, now there is a legacy. And that's one thing I get to do, say, as a teacher, that I have 5,000 students, that some of them actually will take heed of what I said and go and do stuff. And it'll be partly because of what happened in this class. Believe it or not, it's already been that way. So I know if I die tomorrow, it's like I did something. And that's the way that Vera Rubin lives on. And that's the way that you can live on. You don't have to be a teacher. You just need to be a mentor. Like if you're a really amazing lawyer and you mentor other lawyers, that's your legacy. That'll outlive you. So think about that. We did this one. We're done with this sheet now. We did the law of signs. We finished that. I got to this point and the student said today, well, now what do I do? Well, at this point, you just cross multiply, you guys heard of cross multiplication. So like, for instance, you'd have 200 times sine of 60 equals T2 times sine of 70. And then you'd find out T2. You do the same thing with T1. Oh, and the last thing I wanted to talk about on that one was, did you realize this? Saw this on Facebook yesterday, that the bridge that crosses the Mississippi in Memphis has a truss issue. One of the trusses is cracked, and they just shut the whole bridge down. That means that on I-40 you cannot go east. That's kind of a big deal. It's not like you can just go 5 miles and go around it. This is the Mississippi we're talking about. So that shut down traffic, not for today and tomorrow, for a month or 2 or 3. Now I-40 is essentially shut down because of a truss problem, because of this right here, because of that physics. Somebody did not get their free body diagram correct, or they didn't inspect it enough. It was an old bridge. And part of our infrastructure issues in America, you want to have a job for sure for the next 50 years, become a civil engineer. We are going to desperately need your help. Oh, there it is, my guest key. All right. The rest of this hour, we're going to talk about friction and the chemistry of friction. So Miranda, her ears should perk up. She's a chemistry person. Some of you others I know are looking at chemistry as a possible. Miranda, you here? Yeah, Miranda's here. So other people that are into chemistry, we're going to talk your subject today. I taught chemistry for 12 years. I taught chemistry, AP chemistry. We built the program up, accelerated chemistry. We had honors chemistry. And then I taught Chem 3 for a couple of years. And those kids took Chem 3. It was like AP Chem 2. It was like the second year of AP chemistry. Every one of those kids got 5s on the AP chemistry exam. That was a bright bunch of kids. And then it was too expensive. We had to drop it. Plus I started teaching physics. So they dropped the AP Chem or Chem 3. Here we go. This is 6.8. A kid asked me this morning, said, Mr. Askew, we ever going to finish packet 6? We got to get to 615. And obviously, no, certainly not during the year. We will finish it in June and then some. We're going to get on to much bigger things with packet 7. We'll get into power and machines and all that kind of stuff, all the cool stuff. The further you go in physics, the cooler it gets. But every packet gets better. Anyway, so we will finish packet 6 and start packet 7, get into packet 7 in June. All right. Anyway, we'll do 6-8. We'll do this one today, tomorrow. We'll be done with 6-8. 6-9. We'll skip 6-10 because that's gravity. We'll do a little bit with it, but we'll mostly skip it. Then we'll do 6-11. That's impulse. And then we'll do 6-12. That's back to inclined planes. And then maybe, but I start to doubt that we'll ever get to 6-12. 6-13. That gets back to pulley systems. And then anyway, that'll probably be this summer. All right. So here we are. We're going to spend the next 25 minutes talking chemistry. Now for this one, you'll need 2 color pencils. You at least need your pencil and a colored pencil. You can do a pencil and a pen or something, but 2 colors. Otherwise, this is going to be worthless. All right. So first thing we're going to do is we're talking about the bottom of my shoe. This is 2 surfaces, the bottom of my shoe versus the top of the tile that I'm walking on. Okay. So we're going to blow this up to the picometer scale. Now that's a trillionth of a meter. And at picometer scale, you're inside an atom. All right. So we're talking protons, neutrons, electrons. Now tomorrow we'll take it out to the micrometer scale, millionth of a meter. But right now we're talking trillionth of a meter. And we're trying to understand how friction works. Okay. There is a person who discovered friction, who discovered how it works. And we'll talk about him a little bit as well and the tragedy that occurred. All right. So I'm going to make the bottom of my shoe sole red. So yeah, it's polymers, right? But I'm not going to draw out the benzene rings and stuff. I'm just going to say, okay, in general, here we have nuclei. And I know, yes, there are neutrons in there, but I'm not going to waste my time drawing the neutrons because they play a role in the mass, but they don't really play a role in the charge. They are neutral, as James Chadwick discovered in 1932, an English gentleman. It's weird. We discovered the electron first, right? J.J. Thomson, 1895 or 1897. Then in 1912, Rutherford discovers the protons, him and Marsden and Geiger. And then in 1932, it wasn't until 1932 that James Chadwick discovered the neutron. Mainly because the neutron's kind of hidden because you cannot mess with it with charge. You cannot put it into a magnetic field and it doesn't do anything. All right, so leave a gap. Now I'm going to go to the bottom. And the bottom, I'm just showing the nuclei here. The bottom is the top of the tile. So I'm showing the top of the tile, and I'm just randomly putting in some nuclei here. This comes from me from a discussion with Stan Neely. Now, Dr. Neely, I think he's still around. He's retired a long time ago, but he was the head of the chemistry department at OU. And I had him for PChem. And me and my buddies were up one night, like 3 in the morning, when you get those 3 in the morning thoughts, and I was going, hey man, like we were doing this kind of thing, and hey man, my hands, they're not even touching, it's just electron fields, just electron clouds are hitting each other. I can't even touch my hand. And so, my buddies, what the, and so then that got us talking about it. And then the question came up, wait a minute, that makes sense that you have the second strongest force in the universe keeping my hands from touching electron. Oh, we got to draw the electrons. Now, the electrons, I realize, Miranda, don't get mad at me. I realize that they are in levels, but I'm just going to randomly show them. I'm explaining this the way that the head of the chemistry department explained it to me. Okay, so me and my buddies are sitting there going, that's crazy that you really can't touch anything, because the electrons, it's just all you're seeing is electron repulsion, and that's what you're feeling when you clap your hands. But then we got to thinking, if that's the case, how the heck does anything stick to something else? How is there friction then? A block sliding down a ramp. Why is there friction? If it's like, I would think if it's like electron repulsion, it would be like air hockey table, because you're riding on a sea of electrons, on this cloud of electrons. Down here I'm putting, hey, put a gap in there. Put a gap. As they would say in England, mind the gap. You need to have a gap, because there is that zone where the electron cloud's saying, get away, stay away from me. And like I say, these are all complicated. There's a whole crystalline structure here I'm not showing, but we're trying to look in general here. This is something that was discovered around 1939 by a Jewish man named Fritz London, who you probably never heard of, for 3 reasons. 1, it was 1939. 2, it was Germany. 3, he was a Jew. 4, the Nazi propaganda machine basically just called it all fake news. You can't have a Jew, which there are tons of them that were brilliant. You cannot have a Jew coming up with something, so they buried it. Isn't it crazy that a political party would deny science like that? I don't know. It would never happen again. Okay, we learned our lesson, right? All right, so here is the red generalized molecules on the bottom of my shoe is standing on top of the green tile. Of course, electrons aren't really green, but so this made sense to me. And so I went into Stan Neely the next day, and he had office hours. He's really good. I'll tell you, you want to get in good with the professor, start hanging out at their office hours. They are obligated. Most of the time they sit there by themselves, but you're paying for it. They are obligated to help you and be respectful of their time, but it's their office hours. So I started bugging him all the time, and he got used to me after a while. So I gave him my thing. I'm saying, so, Dr. Neely, let me explain. I don't understand how I get electrons, right? And impulsion. How the heck does this phone Why doesn't this, that's a real slick book. Let me find something like this. Okay. Why then doesn't this phone, it's sitting on Velcro. Oh, the calculator. Calculators are really good. There's a whole industry with calculators. Why doesn't that, that's a good one. Why doesn't that calculator slide now? What is, there's not glue there. What's causing that calculator to stick? And he said, that's when he started drawing this up. And I said, okay, now I'm trying to recreate this conversation we had. Now, what's going to be moving? And I can ask you these questions too, and you can answer me here. The protons or the electrons? What say you?
Protons.
The protons are like dump trucks. They're like huge. A couple of things about proton. A proton is 2,000 times 1836, 2,000 times the size, the mass of an electron. So protons and neutrons are huge. It's like dump trucks versus BBs. So thing is, those dump trucks aren't going to move. And the other thing is they're attached in a crystalline structure. If it's a solid, they're attached in a crystalline structure to other atoms. And so they're stuck. Electrons, though, Heisenberg uncertainty principle, right? I don't know where those electrons are. They're moving all the time. Okay. So electrons are all, if the electron has to move, right? It's always gaining energy, losing energy. Basically, all of chemistry is follow the electron. That's basically it. Electrons being shared, electrons being transferred, skewed one way or another. That's it. It's not really the neutrons. The neutrons or protons. That's nuclear physics. That's a whole other ball game. But just basic chemical engineering is always ask yourself, what's happening to the electrons? Electricity, electrical engineering, it's all electrons, you know? So it's the electron that's doing all the moving around. Fair enough. Okay, so electrons are moving around. Now, you tell me, let's throw out your ideas. Why is that red surface on top sticking, sort of, like this is, like the calculator? Why is that sticking, quote, sticking to the green tile? What are your ideas?
Uneven distribution of electrons in the cloud, and they're moving around.
Anybody got an idea?
The uneven.
Oh, wait. Sorry. Okay, now say it.
The uneven distribution of the electrons in the electron cloud, and they're moving.
Okay, Miranda's saying something. I think it's Miranda talking, saying something about the distribution of the electrons. Is that? Hold on a minute, Miranda. Come on, man. I want to give me. I can't use more than one screen. That's killing me. Okay, that was Miranda, I guess. But let me open you up again. Okay, so gotcha. Now I can see who's talking. So Miranda, you said something about the distribution of electrons. Now speak a little louder and let me hear it.
They're moving around.
Yes.
In the cloud, so it's the uneven distribution that causes partial charge.
Okay, stop. Miranda's going to teach the class now. I figured she already knew this. Daggone it. All right. So the electrons, what she's saying that, okay, and she cannot say anything else. She's saying that these electrons are moving around, and even though the whole thing's neutral, if I'm Tiny Elvis and I am walking in here, these electrons are in layers, right? I mean, it's called the Electron Shield. And for all intents and purposes, there's like 7 shields. If you look at the periodic table, 7 levels, right? So about 7 shields. So on more complex, there's at least 4 or 5 a lot of times for these metals, transition metals and stuff, have these shields. The neutrons and protons of the nucleus are shielded from the outside world by all these blankets of electrons. But like Miranda said, those electrons are jumping, doing quantum leaps, right? Between levels, they're going up, they're going down, they're moving around. Heisenberg uncertainty, I don't know where that thing is. And so we could have a situation where randomly there are a couple of electrons that are now moving out to here. And then she said something really important. She said that causes a partial charge. Now, this is the symbol for partial charge. It's a lowercase delta. It looks like somebody was writing the number 8 and kind of got lazy. Okay, like that. So it's a 8 that's been opened up, and that, whoops, that would, I had wrong. That's partial negative. Hello. More negatives. There's more negatives in that area than there are positives. Then that nuclear positive force that emanates, second strongest force in the universe, shielded by levels of electrons. But I could have a situation where randomly, because of the energy of the situation, electrons move more in this area. And so if I'm walking along here, right along here, I feel a negative feel right there. And so that makes this, okay, that makes this wah, wah, wah. For just that little area, it makes that little area negative, in this case, negative, right? Negative. Okay, now what's that going to do? And besides Miranda, Shardy knows this, but what's that going to do to the green surface? We now have this negative area that just randomly happened to happen on the top surface. What's that going to do to my green bottom surface?
Would it attract it or bring it closer together?
Okay, so you would think, and this is what I said to Dr. Neely. I said, oh, he said, so he asked me. I said, ask you then what's going to happen. I said, oh, well, this protons come up here. He looked at me. I said, he said, no, idiot. Look, that's not the case. Why won't that happen? Dr. Neely he got impatient with me. That's why I don't get impatient with you guys, because I know the feeling. Teachers used to be the bullies, man. It was the teachers that were the bullies. I don't know how kids learn anything. So he said, no. Kind of shook his head. Have you learned anything? He said, all right. So remember, the protons are like dump trucks. Plus they're in a lattice structure. They can't really move. Relatively speaking, they can't move. So what's the only other thing that could happen if you have this negative field up here? If this whole area is negative, what's going to happen to these electrons?
I was thinking it would repel.
They are light. 10 to the negative 31st kilograms. Those things are teeny tiny, like I say, like BBs. And so this one's going to go, wait, something ain't right, and it's going to get out of there. It has this negative push from above, and it goes down here, down to a lower level or some other atom, because especially if it's somewhat metallic, it's got a sea of electrons or delocalized, those valence electrons. And so that then is going to make a wah, 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 a negative, a partial, that weird looking 8, a partial positive field down there, because there are now fewer electrons than there were a microsecond ago. Boom, we have an attraction. Now, what some kids will always say is, oh, the reason is an electron from the bottom jumps to the top, and that forms a bond. No, that doesn't happen. It does happen if you're like folding socks. Like you're doing laundry, right? You hope you're all doing your own laundry by now. I hope you're not making your mom or dad do it. But say you're doing your own laundry and you're folding, you pull the socks out of the dryer, you pull them apart. What happens?
They're static.
Unless you're using bounce sheets or something, that's a whole nother deal. But they're mostly static. And so if you do it in the dark, if you do it in pitch dark, next time you do pull your socks apart, you'll see the sparks fly. That is electrons jumping the gap. But as I'm walking along the floor, there's not sparks. So in general, friction is not, yes, spark plug, yes, there's sparks. You walking along the carpet in socks and touch the door handle, boom, you get shocked. That sparks. Lightning bolt from the sky, those electrons are connecting, but that takes 1,000,000 volts. So we don't have that kind of voltage between the bottom of my shoe and the top of the floor. And so, no, that's not what happens. And so what Sophia said was, these electrons start to migrate away from that area, and we've just created a LDF. An LDF. And that stands for, Miranda, you want to take it from there? That stands for what? Do you remember this? You know this, right?
London dispersion.
A London, that stands for a London dispersion force. I've always thought that should be the name of a band. So if Eric gets back into music and decides to start playing a sax in a garage band, all I'm asking is that you call yourselves the London Dispersion Forces. I think it's a great name. You'll be like, hey man, hey, the LDFs are playing at the Opolis this weekend. Oh, you gotta go. Now, Miranda, I'm going to be really impressed if you know why it's called London Dispersion Forces.
After one of the people.
Hold on. Let me turn you up a little bit. Okay, say a little louder.
Is it about named after one of the people, or
It is named after it is named after who discovered it. I didn't know this either. I didn't know it until about 10 years ago. This is named after Fritz London. Fritz, love that name. Fritz London. Fritz London was that Jew I was talking about in 1939-ish. Discovered this between surfaces. He explained friction. Don't you think that's kind of important? Nazis buried it because they didn't want to, they didn't want a Jew to get a Nobel Prize. That's what happens when politics and science combine. It's a bad combination. So Fritz London was unheard of until about people started finally giving him his credit after he died. You could not get the Nobel Prize when you're dead. It's too bad because this is one of the greatest discoveries. He showed this London dispersion, and then they finally named it after him. Thank goodness. I knew it was called LDFs. I didn't know why until I finally looked into it. And I'll put a little bit on him. I'll put a screenshot on him. So London dispersion forces. So let's say that on down the line, what do I got? It's 3 minutes. Okay, on down the line, let's say that at this point, oh man, I wish I taught chemistry again. But I love chemistry. But the thing I loved about chemistry was the physics of it. P-Chem. No, I should have majored in that. So let's say here, this electron goes up here. And this electron goes up here. Well, that's going to cause these negative electrons to come up and be induced. This is called induce induction. This is induce. When you induce a charge, you're forcing those electrons. These electrons on top here did it randomly because of Heisenberg uncertainty. They just happen to be up in here statistically, and that induced these electrons to come up. So like my wife, our first son, he wouldn't come out, and they had to induce labor. They give you progesterone. Don't ever, if the doctor says we're giving you progesterone, say no. So I'm going to wait. And let's wait another week, okay? Because that is not a pleasant birth. But that's inducing, okay? Inducing labor. Here I induced a charge. Here, that's going to give me partial negative down here, partial positive up here. And that's going to cause an attraction. It's not a bond, it's an attraction. This idea of partial charges comes from, well, like say water molecule. That's what gives water all of its power, is that it's got that 105-degree bend, right? And that's what makes water so dangerous. Because if you're walking along, you're tiny Elvis, you're walking along down here, you're going to feel the negative end. That's those lone pairs. You're going to feel the negative end of that water molecule. If you're walking up here, you're going to feel the positive end. Even though water's neutral, it's a dipole. It can flip, it can attack you from either way. And it's small and versatile. That's what makes water the most dangerous molecule. The most feared molecule in the world is water. Given enough time, it'll dissolve anything. So back to our friction situation then. All up and down the line, last thing here. If my foot went from Norman to Dallas, if it was that big, then I would have like maybe 10 LDFs in Purcell, 50 in Ardmore, 30 in Gainesville. So I'd have all up and down the line, I would have these London dispersion forces, and they don't snap together, but they attract, which allows me to push off the floor. If it was a surface that was more slick, maybe I don't have 30 in Ardmore. Maybe I only have 10, because the way the electron structure is on those polymers, they lend themselves to move around more than others. And so things are more sticky. Like for instance, the little, if I'm a chemical engineering, I got tons of patents. See these, the little feet on this guy? Check this out. I put this calculator on here. It's a TI 84 plus. Look at that. This is called angle of repose. We'll talk about that tomorrow. Where it starts to slide is angle of repose. Well, that's probably 30 degrees. Whereas a cheapo calculator, say my phone with Velcro on it, it slides very quick at 10 degrees. But phone cases, calculators, tons of money in London dispersion forces. Okay. And now we are out of time. All right, so don't worry about that for homework. We'll come back to it tomorrow. Your homework is to finish your blue points, turn those in by tomorrow night. But tonight, 7 to 7:45, come get your cheddar here. We're going to get some points for flashback. All right, so that was a good one. Lots of things. Learning about friction, pretty important. All right, so stick around if you got a question. Otherwise, I'll see you tonight at 7.
Mr. Askey, I have a question.
Yeah.
So next year, could juniors join the robotic club?
Yeah, we're starting in October. Yeah, so we'll start up again in October. I'll do it next year. It'll be my last year, but I will sponsor next year. Yeah, and then as a senior, you'll be a junior next year. Then as a senior, I'm grooming Jeremy Ralston. He's a really good mechanics guy. I want him to take over for me, and he'll be really good for when you're a senior. But yeah, we're going to start that up in October.
All right. I was
All right.
thinking.
All right. Talk to you later. Okay.